All right, if you're in the data world, you've definitely used pandas. It's our trusty Swiss Army knife for data analysis. But what happens when your data gets, well, big? When projects grind to a halt and your laptop just can't take it anymore? That's the big question we're going to tackle today. When and how to make that leap from the cozy world of pandas to the massive power of PySpark. Let's dive in.
You know this sound. We've all been there. You kick off a script, the data set's a little beefier than usual, and suddenly your laptop fan spins up like it's clearing for takeoff. And look, this isn't just some funny meme, it's the actual physical sound of a single computer hitting its absolute limit. It's the first big warning sign that you might be asking too much of your tool.
And then it happens. The final boss. That dreaded out-of-memory error. The one that brings your entire analysis to a dead stop. This is basically pandas throwing its hands up and saying, nope, I literally cannot fit all this data into your computer's RAM. And that's not a bug, it's a feature of its design. We've hit a wall. And to get over it, we need a completely different approach.
Okay, so here's how we're going to break this down. First, we're going to define exactly what that pandas memory wall is. Then, we'll introduce PySpark, the engine built for this exact problem. After that, and this is the cool part, we'll look at an amazing bridge between these two worlds. We'll also cover some super important performance tips and hidden gotchas you need to know about. And finally, we'll wrap it all up into a simple, actionable playbook for you. All right, first up, let's talk about the tool we all know and, well, mostly love. To really get why pandas has limits, you have to understand what makes it so awesome in the first place.
I mean, there's a reason pandas is the cornerstone of data science in Python, right? The API just makes sense, it's so intuitive, it's absolutely perfect for datasets under, say, 10 gigs. And it plays so nicely with everything else in the ecosystem, NumPy, Matplotlib, scikit-learn. It is the undisputed king of prototyping and just exploring your data quickly.
Okay, but this table, this is where the story changes. At 1 million rows, pandas is in its element, super efficient. You push it to 10 million, and it starts to sweat a little. It's approaching its limit. By the time you hit 100 million rows, you're in Crash City. It's unstable, it's going to fail. And 1 billion? Forget about it. It's just not possible. And you can see, this is exactly where PySpark takes over and really starts to shine.
So what's really going on under the hood here? Why does this happen? It's simple. Pandas is designed for single-node, in-memory processing. That means its whole strategy is to load the entire dataset straight into your computer's RAM. That's what makes it so snappy on smaller data. But its greatest strength is also its greatest weakness. That memory wall isn't a bug. It's literally baked into its DNA.
So, if pandas hits a wall, what's on the other side? Well, that's where PySpark comes in. It's an engine that was built from the ground up not for one computer, but for a whole fleet of them working together.
And when you put them side by side, wow, you can really see just how different their DNA is. Pandas is eager. It runs a command the second you type it. PySpark is lazy. It plans things out first. Pandas is stuck with the RAM in one machine. Spark uses the RAM of many machines and can even spill over to disk if it has to. And this last one's huge. Spark is fault tolerant. If one computer in your cluster goes down, no big deal. It just recomputes the missing piece. With pandas, a crash means you're starting all over. Okay, I want to zoom in on this lazy execution thing, because it's a total game changer for performance. Think of pandas like a contractor who lays one brick, then the next, immediately. PySpark is like an architect. It looks at the entire blueprint of everything you want to do first. It figures out the smartest, most efficient way to build the whole thing, and then it starts executing. This avoids tons of wasted work, and it's a huge reason it can handle massive scale.
All right, so PySpark is obviously super powerful. But let's be real. The syntax is different. There's a learning curve. What if you could get all that Spark power, but with the familiar, friendly API you already know and love from pandas? Well, turns out you can.
This, right here, is the aha moment. This is what changes the game. That one line of code you've typed 1 million times, import pandas as PD, you just add one little thing. Import PySpark pandas as PS. That's it. With that tiny change, you're telling your code, hey, stop trying to cram everything onto my laptop. Go use that powerful distributed engine instead. It's incredible.
So what is this sorcery? What's actually happening? It's called the Pandas API on Spark. Think of it as a brilliant translation layer. You write the Pandas code you already know, and this API translates it into super optimized jobs that run on the powerful Spark engine in the background. You get the best of both worlds, a syntax you're comfortable with, and execution that can scale like crazy. Okay, this sounds almost too good to be true, right?
Just change one line of code and boom, you're scalable. But is it really that simple? Let's get into the details because, like with anything this powerful, there are some trade-offs and, you guessed it, some hidden gotchas.
Which brings us right to the heart of it all, the big question for this whole explainer. Is this thing actually the same as pandas? And the short answer is no, not really. It looks and feels the same on the surface, but underneath, it's a completely different beast. And thinking it's a perfect one-to-one replacement is how you get into performance trouble.
Let's start with the good stuff, the pros, because there are some huge ones. The learning curve is almost flat. You can take your existing Panda scripts and get them running on huge datasets with just a few tweaks. You get to use all that muscle memory, all that familiar syntax. Over 83% of the functions are there. It's an amazing on-ramp to big data.
But, and this is a big but, you've got to know the gotchas. You can't just ignore the fact that you're running on Spark. You still have to think about clusters and things like that. And more importantly, some operations that are cheap and easy in Pandas are incredibly expensive in a distributed world. And the number one villain here is an operation called the shuffle.
So, what in the world is a shuffle? Think of it like this. Your data is split up across a bunch of different computers. A shuffle is any time that all of those computers have to talk to all of the other computers to get something done. Sorting is the classic example. To find the true order of all your data, every piece of data has to be compared with every other piece. That means sending tons of data across the network, which is super slow. So a simple little .sort_values can bring a massive cluster to its knees.
Okay, now check this out, because this might actually surprise you. You'd think Spark only wins when you have a big cluster of machines, right? But look at this chart. Even on a single powerful laptop, the Pandas API on Spark can actually be faster than regular old Pandas. How is that possible? Well, Pandas is mostly single-threaded. It uses one CPU core. Spark was born for parallelism. It'll light up all the cores on your machine. So even on one computer, that multi-core power can make a huge difference.
Okay, so we've covered a ton of ground. The problem, the solution, that awesome bridge API, and the sneaky gotchas. Let's pull this all together into a simple, clear playbook you can actually use on your next project.
And this right here is a super common pattern you see out in the wild. People aren't really choosing one or the other. They're not enemies, they're partners. You use the speed and flexibility of Pandas to prototype and figure out your logic on a small sample of data. Then, once you've nailed it, you flip the switch and run that same logic at scale with PySpark on the full dataset.
So here's a simple way to think about it, kind of like a tiered system for your data workflow. Tier 1, if your data is under 10 gigs, you're prototyping, just use Pandas. It's the best tool for that job. Tier 2, data's getting bigger, maybe up to 100 gigs, but you're still on one machine, a multi-core library like Polars might be your sweet spot. Tier 3, you know Pandas and you need to go distributed, the Pandas API on Spark is your perfect bridge. And finally, Tier 4, for the massive enterprise-level pipeline streaming data, terabyte-scale jobs, that's where you go with native PySpark.
Look, at the end of the day, it all boils down to this. There's no single best tool for everything. It's about knowing the size and shape of your data, understanding the trade-offs you're making, and then picking the right tool for that specific job. So now you get it. You've seen the bridge from single node to distributed computing. The kinds of questions you can ask and the problems you can solve are no longer limited by how much RAM you can stuff into one machine. You've made the leap from your laptop to the scale of the cloud. So the only real question left is, what are you going to build with that power? Thanks for tuning in.